Hello, I'm Maury Wright, Editorial Director of EDN Magazine, and I'd like to welcome you to a video presentation of an EDN design idea. Design ideas have long been one of the most popular parts of EDN Magazine, both in print and on the web, and now we're happy to offer you a video presentation of a design idea. And now it's my pleasure to introduce Mark Thoren, Application Engineering Manager of the Mixed Signal Products Group at Linear Technology.
Every electronics lab needs a couple different types of voltage sources. Power supplies are obvious, you've got to power your project, but a lot of applications or a lot of circuits you also needed some sort of DC voltage or accurate DC voltage source. And a lot of times a power supply gets used because it's the only thing around, but they've got a couple of drawbacks. They're not very stable over time and temperature, they can't sink any current, and it's very hard to set an accurate voltage even if you've got a 10-turn adjustment. So what you'd really like to have is something like this, a voltage standard. This is a Fluke 332 that's about 40 years old, and what's nice about this is it's got one part in 10 million resolution and still working strong after 40 years, but it does take a little bit of time and effort to keep up and running. So what you'd really like is something halfway in between. One thing that comes to mind is a precision potentiometer that reads directly with a voltage reference and a suitable output buffer. Most pots will give you about 1 part in 1,000 resolution, which is good enough for general purpose use. And the ultimate would be a 7-decade Kelvin-Varley divider that will give you 1 part in 10 million resolution. To design a reference and buffer for this is a little prohibitive, though. It's a very accurate device. Something that's right in the right range of accuracy is a 5-decade Kelvin-Varley divider. This will give you 1 part in 100,000 resolution, and all it would need is a suitable reference and a suitable output buffer to make a very nice lab instrument. So a reference and a buffer on a potentiometer is not a terribly difficult circuit, but there's a few features that it's nice to have. So we start out with an LT1236 accurate 10-volt reference with a trim circuit. Power is from 12 AA cells, which is nice because their batteries are very quiet and there's no way for line noise to conduct into your circuit. I've got a low battery indicator, and what this does, if the battery voltage drops below 11.5 volts, that's the dropout voltage of the 1236 reference, so the green light turns on continuously. I've also got a low duty cycle pilot light that pulses for a couple of milliseconds every 2 seconds, and this reminds you to turn the box off at the end of the day so you don't burn up all your batteries. This is the Kelvin-Varley divider or potentiometer, and it's buffered by an LT1881 buffer. There's also the ability to switch in an LT1010 buffer to greatly increase the output drive capability and ability to drive capacitive loads. And this is switchable to go between what I call turbo mode and low power mode. This burns an extra 10 milliamps of supply current, so this lets you trade off output drive for battery life. So to tell whether or not the output is sinking or sourcing too much current, we take a current mirror, 100 microamp current sink and 100 microamp current source, and set up a plus minus a couple of millivolt adjustable window around the output voltage. We compare that with a second opinion of what the output voltage should be, and if the output voltage gets dragged outside of that window, it will turn on either a blue light or a red light, depending on whether the output is sourcing or sinking too much current. So if there's no lights turned on, then you know that the output voltage is what you've set the potentiometer to. So this is the first prototype of the circuit, and here it is in a nice instrument enclosure, a recycled hard drive case. So as you can see, we've got 5 volts set on the dial and 5 volts exactly on the output. 6 volts, 7 volts, 3 volts exactly. Switching in by decade, 3.11. So you can see where this would be useful in testing an op-amp circuit. Okay, so some of the other features, if we give it a 100 ohm resistive load, which should pull 50 milliamps that the 1800 can't deliver, we get a sourcing too much current warning. Enable the 1010 buffer in turbo mode here, and it's happy again. Similarly, sinking too much current, which we can drive some current, drive 50 milliamps into the output from a power supply. And we get a sinking too much current warning that the 1010 takes care of. And the LT1881 doesn't really like to drive capacitive loads, so if we give it a 0.1 microfarad capacitive load, you get a nice purple warning light. Both the red and blue on alternately, and turbo mode takes care of that too. I hope you found this useful, and one word of advice: if you do build this device, build two, because someone else in your lab will surely walk off with it.
I'd like to thank you for watching this video presentation of an EDN design idea and invite you to please contact me via phone or email with any comments or feedback.